Hello, hello. Happy Thursday, everyone. Really happy to be here with all of you today. We are just at the top of the hour, so we're going to go ahead and get started. My name is Heather Grant. I am one of the community admins here at the Maintenance Community by Upkeep. Thank you all for making the time to be with us today. If you are not already a member of the maintenance community on Slack, we would love to have you join us. I will drop a link to sign up in the chat in just a moment. Today we have James from Eruditio joining for a presentation on using the PF interval. I'll turn it over to James to introduce himself in just a moment, but I know it'll be a great conversation today. The recording from our session will be available in the maintenance community on Slack tomorrow, along with a copy of the slides that you see here today. And James himself is actually also available to answer questions live in the Slack group. So please feel free to share the recording of this webinar or the invitation to Slack directly with friends, colleagues, or anyone else you know who would benefit from hearing some of James's expertise. Last piece of housekeeping, and then we'll go ahead and get started. You'll notice that your cameras and microphones are not turned on today. So what you'll want to do if you have any questions for James as we go throughout the presentation is use that chat feature on the right-hand side of your screen. We'll monitor questions as we go throughout the presentation today. And then anything we don't answer during our time, we'll answer at the end of the session. Again, then anything that we don't answer during our live webinar, we will answer offline as well. That is it from me. Thank you again, everyone, and James especially, for being here with us today. And I will turn it over to you to get started.
All right. Thank you, Heather. Welcome, everyone. Today, we're going to talk about using the PF interval, and specifically, how do we drive strategy optimization using that PF interval. All right. So welcome. As you have questions, feel free to throw them in the chat box, and I'll do my best to answer them as we're going. And then we'll have some time at the end to answer any other questions that we miss. For those of you that I have not had the opportunity to meet, my name is James Kovacevic. I'm a principal instructor with Eruditio. I've been involved in maintenance and reliability for about 17 years now, working in North America, South America, spent some time in Africa, Asia, and the Middle East and Europe, implementing work management, spares management, or reliability engineering programs. Aside from that, I got 3 young kids, beautiful wife, and 2 crazy dogs that kind of keep us busy. And yeah, the only other thing I'll mention is if you're interested in learning more about all these topics, I do host a weekly podcast rooted in reliability. You can find that on iTunes, Stitcher, Spotify, and a bunch of other places. And it's not just me. I bring on all the industry experts to talk about the various topics. All right, enough about me. Let's talk about the PF interval and how we want to use that to drive improvements in our maintenance program. All right, now, before we dive into the PF curve and the PF interval a little bit more specifically, we need to understand, are we being effective with what we're doing? All right, so the PF interval is going to help us, optimize frequencies, what we're doing, that type of thing. But first, before we do that, we got to ask, are we being effective with what we're doing from a preventative or predictive standpoint? What I mean by that is, can we identify the unique failure mode we're trying to prevent or predict? Are our inspections repeatable and able to detect that unique failure mode? If we can't identify that unique failure mode and our inspections are not unique or repeatable, the PF interval isn't going to make a difference. I'll give you an example. So if we have a pump and we have a PM that many organizations have for pumps, and it says inspect pump, what are we actually looking for when we go to inspect a pump? One mechanic may go in and they're going to look at the seals. They might get the screwdriver and listen to bearings. They may look at a variety of different things on that pump. Another mechanic may look at it and say, it's still there and it's running. We're good. Let's move on. If we are not effective in being able to identify the unique failure mode we're trying to prevent, and we're not making that inspection repeatable, the PF interval isn't going to help us. It doesn't matter at this point because we don't have a basis to set that moving forward. All right. So we got to get detailed. We got to get to the failure mode level again. Now, just in case people are not familiar with the failure mode, I'm going to break it down the way I typically do, and I want to look at the part problem cause typically. So a bearing, for example, there may be multiple problems we can experience with a bearing. It might be seized, it might be worn, it might be damaged, it might be corroded, and so on and so forth. Now, each one of these problems that we have could be driven by a number of different causes. So for example, if it's worn, it could be due to contamination, due to incorrect fit, wrong lube type, and so on and so forth. End of life even. If it's damaged, we installed that with the good old precision torch and hammer maintenance approach, and we damaged it putting it in. Could have over lubricated it, under lubricated it, and damaged it that way, and so on and so forth. The reason why we need to understand this is going to allow us to implement the right inspection at the right frequency using the PF interval. All right? So we got to understand our failure modes first. Once we got failure modes, then we can worry about the PF interval. Now, where does the PF interval come from, and how does that fit into an overall maintenance strategy? Well, I want to take a couple steps back still, and let's talk about how we've come to understand the PF interval. So let's talk about functions first. Now, the primary function of an asset is the reason why we bought that particular asset. In this example, we have a blower, and that function is to move clean, dry air at a rate of 12,000 CFM. If there's an upper limit, we want to put that in there, so between 12,000 and 15,000 CFM. That is not the design specification, but what the process needs to operate. Now, we may have secondary functions as well, and we can go ahead and list those, but my primary focus right now is just that primary function. Now, we may have functional failures, and that is when the asset is not able to meet the performance specification spelled out in the function. In this example, move less than 12,000 CFM. So if we're at 11,999, it is a functional failure. We're not meeting the needs of the system. Now, I'm sure many of you know all these terms, but I just want to make sure everyone's on the same page before we start diving into the intricacies of the PF curve. Now, where does the PF curve come from? Well, we have something called potential failures, and there's a couple different definitions if you Google it. And I figured we put these up here to kind of chat through. But the first one is partial failure. Many assets do not fail abruptly, but give some warning or sign of the fact that they are about to fail. Another definition indicates a detectable state of failure or point at which the degradation begins. And this will all be illustrated on the PF curve next. But what's important here is that the equipment is showing signs or it is starting to fail slowly. It is not an abrupt failure. So let's take a look at the PF curve here. All right, so I'm sure many of you have seen this. This one's a little extended. We got the I there for installation. We do precision maintenance. We can extend that I to P interval. But the P point here is the point at which the failure starts to occur. It's the potential failure point. Now, depending on what technology we're using to detect that potential failure, we may get different lead times to failure, if you will, as we progress down the PF curve. You can see early signal 1. We have more time than early signal 2, more time than early signal 3, and so on and so forth before we get to that F point, and that is the functional failure. So going back to our example, that might be that functional failure where we hit 11,999 CFM from our blower. If we continue to let it go, we'll get catastrophic failure. As you can see further down, the cost of repair is going to go up. But this forms the basis of our PF interval. The PF interval is pretty simple. The PF interval is at the point where when we detect, so P1 for example, to the F, the time between P1 and F. And if we're using a different technology, so maybe, for example, P1 we're using ultrasound, maybe P2 we're using vibration. The PF interval will be different for vibration than it will be for ultrasound. And it will be different for each and every failure mode that we experience in there. All right? Now, as we look through this and talk through this, there's a lot of things that we can consider here. All right? There is no defined database that gives us P to F interval data saying if you're using a bearing and vibration, here's how much time from when you detect this to when this occurs. It doesn't exist. Why is that? Well, operating context is very, very different for every single application. Therefore, the P to F interval or time from the P1 to the F or P2 to the F is going to be different. All right. What really this is the PF interval is it's a predictor of remaining useful life from when we detect that early warning signal of something that is failing. All right. Now, let's talk about why we really care about the PF interval and why we want to get it further up the curve. Why do we want to detect it sooner? All right, because that's going to help us optimize our strategy. Now, we all know time is money. All right. So if we have early warning of an impending failure, so in this point, we're going to detect something at P3 here, we have time to plan, obtain the parts, schedule, and then actually perform the work before it reaches a functional failure. And then our mean time to repair on that asset is relatively small because it's only the time to execute that particular work. It's not the time to expedite parts and all that time that the equipment's down. It's only focused on that actual repair time. So by getting further up that PF curve, giving us a larger PF interval, we can plan, schedule, order parts or kit the parts and execute that work in a planned, timely manner. Right? But unfortunately, what we see is a lot of organizations operate in this area here. You can see we have a traditional PM. We identify the failure mode. Now we're condensing and trying to compress all this plan, getting the parts, scheduling the work, executing the work during a planned down period to prevent that functional failure, or we're doing it after we've hit that functional failure standpoint. So to us, we want to extend that P to F interval by being more effective in our inspections, moving further up that curve. If we do it properly, we have lots of time. All right, so we're going to leverage not just predictive maintenance up here, we can also leverage information from our MES or manufacturing execution system. We can leverage process parameters. We can leverage all those things to give us these warning signs or a combination to get further up that curve. The further up the curve we go, the better. But there's a trick here. We have to know when we're going to detect this and how to detect this in a timely manner. And that's where some of the PF interval stuff comes in. And we'll talk about that in a moment. Now, the other thing we want to talk about before we move too far is we have to understand the failure effects. All right, so we're going back to our FMEA roots here. And if we look at our failure effects, we want to understand two things. The immediate physical effects that failure has on the surrounding equipment. All right, so that tells us, the consequence of the failure, that type of thing. But the before or the on condition events leading up to a functional failure. So what does that tell us? It tells us what we need to look for that unique failure mode. So if we have a bearing that's misaligned, what are we going to see with that misalignment? Well, we might pick up some vibration, or if we're doing a potential more intrusive inspection and we're putting, a laser alignment on it, we'll detect it that way. But that's going to give us a little further down the curve. Right? So the on condition stuff tells us what we need to look for. All right, now before I move on, I'm just going to pause for a second. Neil, you have a question. Where does precision maintenance fit in the PF curve? Great question. I'm going to go back for 1 second just to highlight it. Starts here long before that P point. If we install it correctly here, we're going to extend the time from when it's installed to that first P point occurs, or in some instances, you will eliminate that potential failure from ever occurring. If we install it correctly, we'll use alignment again as an example. If we properly align it, we're never going to have a failure mode of misalignment here. So it eliminates some of these, and it will extend the life of that bearing in a variety of other ways. All right. So you have to understand those failure effects, more specifically the on condition. Now, like we talked about, we have to consider detectability when we're using our PF interval as well. All right, we're going to get to in a few minutes how all this ties together, but we have to consider how easy are these failure modes to detect. What's the instrument type we're going to use? Vibration, ultrasound, oil analysis, visual inspections, and so on and so forth. That's going to give us more time, or we're going to be further up on that PF curve. The skill of the technician is another factor we got to consider. If we have a very skilled technician or very skilled vibration tech, we might be able to detect further up that curve. Whereas if we have a very basic, say, ultrasound inspection program in place, we might be further down that curve. Then we have to ask this critical question. Does using that technology or the instrument type and the skill of the technician give us enough time to react from when we can detect it? If we cannot detect it and react in time before potential failure, we have other approaches we need to use, and we're going to take a different approach with the PF interval. All right, so we got to ask ourselves those questions first. Now, Why do we need to do all this? Well, there's a lot going on here that we need to consider. All right, so what's the technology we're using? How do we detect it? What's the lead time to failure when we make that detection? Right? But there's a couple of rules of thumb that we have available to us. What we want to do is be able to detect these potential failures that are occurring using predictive maintenance inspections or potentially a visual or intrusive inspections if there's not a good predictive alternative. Right? So what we want to do is we want to be able to detect that failure. Now, how do we detect or how do we set the interval based on the PF interval? Well, there's a couple examples that I'll give to you guys because there is no database for that P to F interval. We have to rely on experience and subject matter experts if we don't have good data. So if we have a very large, slow-moving bearing, so a 2 or 3 foot diameter bearing turning at 2 or 3 RPM, and that thing starts to get a tiny little noise you picked up through ultrasound or a tiny little vibration picked up on with vibration, how long is that thing going to last? Chances are, because it's so big and so slow moving, it's going to last a long time. Now, however, if we have a very small, high-speed spindle bearing turning at, say, 10,000 RPM, and we start to have a minor defect in that, chances are it's not going to last very long, right? We're talking hours, maybe days. So we have to use experience to help set these PF intervals as a starting point if we don't have good data, all right? Now, once we've established what do we think this is going to be, so we're using, say, vibration to detect this failure mode. How long is it going to take from when we detect to when it fails? Say it's 3 months. Okay, perfect. Now we got a working point. That's our PF interval. Now here's where we start to apply some basic approaches to using that PF interval to set the inspection frequency. First one here that we're going to typically look at is if you don't have good data and you don't have that expertise, you're going to use roughly 1/2 to 1/3 of the MTBF as a starting point for your inspections. So 1/2 to 1/3 of the MTBF. We're going to use that to help us establish how often should we be inspecting. Now there's some other things we can do with some data. Typically, if it's a standard inspection, so not a critical piece of equipment, we are going to want to inspect at 1/2 to 1/3 of the PF interval. All right, so if we establish that, that bearing using vibration, we have 3 months from when it'll start to make a little vibration to when it fails, we will generally want to inspect every 4 to 6 weeks, right? Because that's a standard piece of equipment. However, there's a caveat to this. We have to have enough time to plan, order our parts, schedule, and execute that work before that functional failure. If we don't have enough time for that, we may have to shorten up that interval. So we might have to go to 3 weeks to give us enough time to perform that planning and scheduling or work management function and execute that work. If it's a more critical piece of equipment, we're generally going to want to be a little more aggressive in detecting that failure. So we're generally going to optimize for about 1/5 of the PF interval. So once again, if it's, say in 3 months, what's 1/5 of that 3 months? That's what our new inspection interval is going to be because it's a critical piece of equipment. Right. These are starting points. As we collect data, as we better understand what's going on with our assets, how they're performing, how they're failing, we're going to optimize these over time. But as a starting point, you can use that experience to determine what that PF interval is based on the failure mode and the method you're using to detect, and then use these rules of thumb to set how often should we inspect. One more caveat for you. If we start to detect a defect, we want to start measuring more frequently, all right? We want to increase our inspection frequently while we know there's a defect. One, it gives us opportunity to collect some good data and determine how fast is it to grade in that operating context. But two, it lets us know if our initial assumptions of, say, 3 months is off and really it's only 2. That way we can prevent that functional failure and that maintenance outage on that equipment. All right, we got 2 questions here that came up. We have pump maintenance scheduling. Our running hours are the best way to decide on avoiding cost of failure. How does PF interval fit on pumps? Great question. So pumps itself, we don't want to discuss just the pump. We want to discuss the unique failure mode you're looking for on that pump. So if you have a seal leaking due to cavitation or overheating or something like that, those unique failure modes are what we're going to plug into that PF interval. or PF curve, and then establish those intervals. Right? We don't want to just say at a pump level, we got to get down to those failure modes, because that's what the PF interval is based on, is the unique failure mode and your detection method. All right, with the advent of FMEA-based APM systems and predictive maintenance tools, where do you see fit into the PF curve? How would you measure the efficiency tools based on PF curves? All right, great question. So if we have an API system where we've done our FMEAs, and when I refer to APM system, I'm assuming it's an entire system, not just a software package. We've done our FMEAs, we've identified the failure modes, we've identified severity, probability of occurrence, all those different things, we can start to plug those in. So if we know that this is likely to occur once a year, and once it does start to occur, how long is it going to take to fail, we can start going back and looking at that to establish our inspection frequencies. Now, the efficiency of these tools, well, there's a rule of thumb that we're going to talk about in a little bit, but it's a 6-to-1 rule. If we have 6 inspections, we should be finding an issue at least 1 out of every 6 times we inspect it. We'll walk through that in a moment. But that's a good rule of thumb to also gut check. Are our inspections frequent enough or not frequent enough? That should help us with that. Now, if I didn't answer your question, just let me know. I'll be more than happy to dive in it again. All right. And it looks like there's one more question here. How would system complexity influence the PF interval decision? Okay, once again, we're looking at the individual failure mode. So if we're looking at a complex hydraulic system, the pump failure, what's failing on that pump? Is it we have impeller eroding due to cavitation? Do we have seal failures? Do we have filter failures? What are the reasons why? We got to break it down to that level to kind of establish what that PF interval is and what the inspection frequency should be. Once we have that, then we can package our work together on like frequencies to accomplish those tasks. All right. So continuing on, now we're talking about, PF intervals, but sometimes people confuse PF intervals with mean time between failure, and I want to kind of, set the record straight on that. Mean time between failures is strictly the predicted elapsed time between inherent failures of a mechanical or electrical system during normal operation. Essentially, it's the average time between failures of a system. One of the challenges with this, if we're using just MTBF on a component to establish our inspection rates, is it doesn't differentiate between infant mortalities, random failures, or wear-out failures. It doesn't differentiate between those. So if we're having if we have a wide mix where we have some things that are actually wearing out with life, we have some early life failures and so on and so forth, it's going to skew it, and we might not be detecting all the different things we need to be. So MTBF is an average, but it's generally for all failure modes of a component, not each individual component, where the PF interval is specific to the failure modes. Now, if we use MTBF, it's a starting point, but then we got to put a lot of work behind it to optimize it over time to get the right inspection frequencies. Because let's face it, I have yet to meet a maintenance team that has enough resources. Every maintenance team I've ever worked with says we don't have enough people. So if we're over inspecting, we might not be doing other critical work that we need to be doing. And if we're under inspecting, we're introducing potentially downtime to the process. So MTBF, it's a starting point, but keep in mind it's at a system, not a failure mode level, and it does not relate to the PF interval. So, like I was saying, it does not relate. The PF interval is the timer cycles between the point with the initial detection of the potential failure condition and the time of the actual functional failure. So when we detect to when it fails, whereas MTBF is just the average between all failures on a system, right? So there's a significant difference there. So please don't confuse the two. All right, so once we have used our P to F interval so far, and we've established what we think that P to F interval is based on subject matter expertise, like equipment, that type of thing, we set our inspection frequencies. Now we can optimize that over time. Now this only applies to route-based predictive maintenance activities or inspection activities. This does not apply to online condition monitoring. That's a whole different animal, all right? But this is where we're sending people out to do the work. If we have that initial inspection, after a period of time, we want to start to refine it to optimize that frequency. One of the ways we do that is the 6-to-1 rule, right? This method is there to evaluate PM tasks to identify improvements to either improve the effectiveness or the efficiency of it. All right. Essentially what it says, for every 6 times we go and look for something, we should be generating 1 corrective action. And this is strictly a rule of thumb. It doesn't apply to everything, but it's a good rule of thumb to start with. Now, when we look at this, we want to identify a couple things. Are we detecting or not detecting those corrective actions because of the effectiveness of our inspection, or are we trying to improve the efficiency? So what I mean by that is if I have a PM that is inspect pump, that's not effective because everyone is going to do it differently, and there's no repeatability in that inspection process. So if that's the case, this rule does not apply. We have to have that effectiveness. Everyone's got to be looking at the same failure mode the same way, or we can't evaluate the effectiveness of it. Once we have that effectiveness, then we can look at the efficiency, which is either increasing or decreasing the inspection intervals based on those findings. Now, this 6-to-1 is typically done on a failure mode basis, right? This is why having failure codes in your CMMS are so important. If we're inspecting a bearing and we're finding a bearing defect, what was the cause? Is it aligned with the PM and what we're trying to detect? Then we can start to expand or contract those inspection intervals. Like I said, this assumes that the PMs are effective and everyone is identifying it the same way. It is task specific, all right? So keep that in mind as well. All right, so question came up, does it mean that mean time between inspections or various, therefore would determine the MTBM as not intended to run to MTBF? I think I understand where you're going. Are we looking at mean time between inspections or mean time between maintenance? That I haven't seen applied this way against the PF curve. I've seen mean time between maintenance for calculating, different types of availability, those types of things, but not for optimizing intervals or PF or inspections, if you will. All right, so we can use that 6-to-1 rule to really look at the PF interval and optimize our existing activities. So why do we have a 6-to-1 rule? Well, I'm sure many of you have seen this before, nice even distribution. What we're trying to do is we're trying to capture at least 1 out of 6, or of all the failures, we have 6 opportunities to catch it. Right? So if we only inspect once, all right, on average, we have our life of our asset or component where it fails here at 0. We inspect once before that, we're not going to catch it all, and we may catch it too late or too early. All right. Therefore, we might be changing out components too early or getting way too close to failure or potentially running into a functional failure standpoint. So we want to inspect a variety of times. So if we can inspect 6 times over that P to F interval, we got a 99.7% chance of finding that failure before it results in a functional failure. So that's what we're really aiming for. We want to be able to detect throughout that entire PF interval and have a good confidence that we're going to catch it, right? That's why once we start to acquire data on these failures and we start to have operating context specific failure data for the specific failure modes, we can use various statistical analysis tools to refine that a bit more, right? But in my experience, most organizations don't have that data, so we have to rely on 6-to-1 rules and subject matter expertise when establishing these intervals. All right, another question came up. Is mean time to repair the best way of measuring the effectiveness of a craft, or is a KPI for performance on a performance contract? Mean time to repair has so many different things that feed into it. So we want to, understand what are we trying to do. If we're looking at how our overall logistical system and support system is, mean downtime is probably a good measure that we're going to use. If we're looking at, assuming we have a good logistical support system, meaning we have all the right parts and tools and everything on hand, then mean active maintenance time is probably a better measure, because that includes both preventative and corrective actions that we're performing on the equipment. And that really looks at, when we have the equipment down, how well are we executing against it. All right, carrying on. So really, when we look at this, we want to be looking at and identifying all the potential opportunities for these failures. If we're inspecting too early, we may be changing too early with those underperformers, if you will, and we're changing out way too early. That means we're spending a lot more money than we need to. We got the average area where, you know, we're going to address most of the issues and it's probably a good balance, but we also have things that we're changing too early still, whereas those overachievers, we're going to be able to detect those when they're failing at a later point in their life, minimize the maintenance costs and potential downtime associated with those as well. So that's where the 6-to-1 rule generally comes from. All right. So we really want to go after that type of approach. All right. It's a challenge though, because if we don't have the failure modes, we might be changing certain components because it's an infant mortality issue, not because it's a wear out or the various other issues that we encounter. So that's why it's got to be at the failure mode level. If it's not at the failure mode level, PF interval doesn't really apply. So one of the things that we can do with all this information is we can use it to show operations the impact of extending PM inspection frequencies. So for example, if we have a very long PF interval, we can demonstrate with our data, we can detect it here, plan and schedule the repair here, and avoid all these extra inspections or intrusive inspections or other activities if we have it. All right. More reliable components, as we get more data and we understand what the true PF interval is, this distribution is going to narrow up and we'll have a better idea of how often it fails or what the lead time to failure is. And then we can reduce, or maybe not reduce, optimize our inspection intervals, if you will. So a couple things I want to highlight with the PF interval. The PF interval is the time from when we can detect a potential failure to when the equipment functionally fails. All right. That is specific to a unique failure mode. All right. So keep that in mind. It's not at a system like a pump. It is a bearing, an impeller, a seal, and so on and so forth. And more specifically, the problems that we're seeing on those. The PF interval is detection method specific. So if we have a really strong PF interval based on data for vibration and we move that inspection to ultrasound, that PF interval is going to change dramatically, and we need to account for that when we're shifting our routes around. It's also operating context specific. So if we have a pump that runs 24/7, 365 days a year, we can't directly take that data and drop it into one that runs 24/5. All right, we're going to have to do some work there. We're going to have to revalidate all that data because it's operating context specific. Same thing with the type of liquid we're pumping in that pump. That's going to change these intervals potentially. So you got to keep all that in mind. If we do all of this well, we can optimize our P to F interval over time and optimize our maintenance strategy. With that being said, there are a couple other resources that may help you guys, and then I'll open it up for questions. There's 2 blogs that I've written in the past. One is the PF Curve Revisited, and it talks about the precision maintenance piece, the spare parts piece, and the design piece that really goes to extending that interval, or the PF curve, if you will. And then there's also another approach of establishing frequency of inspections that it's listed there as well. All right. So those are resources you guys can access, and it goes through some of the formulas and so on and so forth to help establish some of those things. With that being said, I thank you for your time. I'll open it up for any questions you guys may have. All right. So Neil, for the same type of equipment installed at various sites, operating with different performances, does a PF interval and inspection interval should be the same? It should not, Neil, unless you guys are very, very conservative. And what I mean by that is you guys are erring on the side of caution and over inspecting. You might be able to get away with it that way, but then you're adding extra resources and costs to your maintenance program. If how we maintain a standby versus a 24/7 piece of equipment, it should be different. Standby is going to have different failure modes than what we'll typically see with a fully operating piece of equipment. That should change dramatically. And that's a challenge in certain large organizations where they're trying to standardize all their maintenance approaches. It doesn't always work. So I would say, it's probably a good starting point. Collect some data and use the 6-to-1 rule to kind of optimize those recommendations or suggestions over time. That's what I would do. Is there a guide or rule of thumb for PF interval for each failure per CBM technique? Not necessarily, unfortunately. If you look at some of the books, they'll say, this type of vibration will give you 2 to 8 months lead time to failure, but it's not failure mode specific. In the back of RCM2 by John Mowbray, he goes through that in detail, but that's 20 years old now, give or take, somewhere in that range. So there's newer technology that either gives us more or less lead time there. That establishing that PF interval, it really comes down to subject matter expertise, experience, like equipment. It's a bit of art and science until you collect the data. The only component I know that actually has PF interval data is lithium ion batteries. It's the only component I know that actually has repeatable PF intervals and repeatable PF curves regardless of operating context. So that's the only component. Everything else, bearings and others, many have tried to establish those databases or PDEF intervals, and they can't make it work because of the varying operating context. In order to know some of the PF time of some failure modes, we will be experiencing failure sometimes. You may experience that, Hector, absolutely. So if we're collecting that data, we may experience failures, but that's why we generally want to start a little more conservative and say half to 1/3 of the PF interval, what we guess that PF interval is, and then use the 6-to-1 rule to refine. That way we shouldn't experience too many, but we're collecting data and we're able to detect that potential failure and start establishing a more accurate PDEF interval time. All right.
All right.
One more question, I guess. Would a Six Sigma deviation application be useful on all components? It would be if you have enough data. All right, if you know that we're having all of these failures, or the lead time to failures is this, we're able to predict that PF interval and we're collecting data to support it, that would help. If at a very high level we're doing it with MTBF, it may help to streamline some of our more generic or less critical PMs. That would definitely work. To me, it would be asset criticality decision. We wouldn't be able to do this on all assets or components. We'd want to focus on the ones that are most important to the organization.
Awesome. Let's see, we have a couple people typing. We'll stall in case it's a question. But thank you, James, for another great presentation. James's contact information is up here on the screen, and he is also available in Slack. I know he's on LinkedIn as well. Pretty active, sharing some great resources. So feel free to find him in all of those places. Still stalling for those people who are typing.
Yeah. If you guys have any questions about this, feel free to reach out. Be more than happy to chat with you offline, or your specific applications. We'll be able to do that. Thanks, everyone.
Awesome. Thanks so much. Looks like it was just a bunch of thank yous, and good job. So we'll end it there today. I appreciate everyone taking the time. See you next time. Bye.
Bye.